In this talk, we discuss monotone contractions. These are functions that are both monotone and contracting, and we look into algorithms to compute fixed points of such functions, as well as some computational complexity related results. We will work with a complete lattice that is defined on d dimensions, and each dimension consists of n+1 points. The lattice imposes a natural ordering on the points. Therefore, starting from a point x, we say that a point y is above x if every coordinate of y has a higher value than the corresponding coordinate of x. Similarly, we say that a point is below x if every coordinate of that point is lower than the coordinate of x. Any point for which this inequality does not hold for each dimension is considered incomparable to x. A function f that is defined from the complete lattice and maps it back to itself is monotone if for any pair of points x and y, the value that f gives to x, so fx, is lower than the value of f of y. An important theorem for monotone functions is Tarski's fixed point theorem. This states that every monotone function in a complete lattice has a fixed point. The fixed point is a point where x is mapped back to itself by f. Therefore, a point x equals to fx. Additionally, a stronger version of Tarski's theorem states that every monotone function in a complete lattice has a greatest and least fixed point. Therefore, this version imposes an ordering of the fixed points in the lattice. Computationally speaking, the Tarski problem can be stated as, given a function f that maps the lattice to itself, either find a fixed point of this function, so a point where x is equal to f of x, or find a violation of monotonicity. Why is that the case? Because by Tarski, we know that every monotone function must have a fixed point. Therefore, if the fixed point does not exist, it must mean that there is a violation of monotonicity for this function. Therefore, we want to find a pair of points that witness this violation. In terms of upper bounds for the Tarski problem, by the theorem mentioned before, we get that the problem is in TF and P because there exists a solution to this problem, which is the fixed point. And this class is the class of problems, total function problems in NP. Additionally, the problem has been shown to lie in PPAT and PLS, and therefore also in CLS, while CLS captures the intersection of PPAT and PLS. These are three well-known subclasses of TF&P. And we can see it here where PLS and PPAT, their intersection CLS is captured here. And we additionally have the class UELPL, which we are interested in this work, and it's a subclass of CLS. In terms of query complexity for the d-dimensional Tarski problem, we know that a fixed point originally, the original algorithm found the fixed point in log to the power of d queries. However, subsequent work has further improved the exponent down to d plus 1 over 2 queries. And all these algorithms run in polynomial time for each query. Now, in terms of lower bounds for the Tarski problem, finding the greatest or least fixed point is an NP-hard problem, which captures the difficulty to solve this problem in general, even for one-dimensional cases. Additionally, in 2 dimensions, there's a log square lower bound to the number of queries required to find the fixed point. Moving on to the second component of the monotone contractions, which is the contracting functions. These functions are defined from the unit cube in d dimensions, that the unit cube is mapped back to itself, and a function is considered contracting in the L-infinity norm if for any pair of points x and x prime, the mapping by f of these points is shrinking compared to their original L-infinity dimensions, distances. Banach's fixed point theorem, which is defined on the contraction functions, states that every contraction map has a unique fixed point. However, the caveat in this case is that this fixed point might have irrational coordinates. From a computational point of view, the problem can be defined as, given the contraction map as an arithmetic circuit, either find an epsilon approximate fixed point or find a pair of points that witness a violation of L-infinity contraction. So where f is increasing rather than decreasing compared to the L infinity distance between the 2 points. Since we know the result by Banach, we place the problem in TF and P. Additionally, the problem has been shown to lie in CLS, which is the same complexity class as we stated for Tarski previously. For a restriction of contractions, which is piecewise linear functions, the problem has been shown to lie in UEOPL, which is the subclass of CLS and is a class intended to capture problems with unique solutions. And additionally, we state that there has to be a trade-off between the query complexity and the running time. Namely, there exists an algorithm that finds an epsilon approximate fixed point in d squared log number of queries. However, it does not run in polynomial time. But an algorithm that does run in polynomial time requires log to the power of d number of queries. Therefore, we see here, we notice the trade-off that we must make. A monotone contraction, now combining these two notions that we previously discussed, is a function that maps the unit cube back to itself in d dimensions and is monotone and contracting in the L infinity norm. So it combines these two properties together. And computationally, if this function f is given as an arithmetic circuit, the problem is to either find an epsilon approximate fixed point, witness a violation of monotonicity, or a violation of L infinity contraction. These functions are interesting because they do exist in practice, and a motivation for this comes from discounted games. Here we have the discounting factor as 0.1, so it must be strictly below 1. And this discounted game is a game that takes place in a graph, and we have two players, max and min, that move the token around in this graph. And max corresponds to the box-shaped vertices, while min corresponds to the circle vertices. The payoff is captured by every possible move between the token moving from along the edges of the graph. And starting from the first point, we get a payoff of 4 before any move takes place. Then max player plays a move and then moves the token to the next node, which is 2. However, there is a discount of the reward for this play. Therefore, we apply the discounting factor for this move. Next, the next player plays, and then there's further discounting for the payoff of this game, and so on and so forth, as long as we progress through the graph and the play in turns. This payoff is won by the max player, and min loses this payoff. So max has an incentive to maximize this payoff, and min has an incentive to minimize this payoff. The value of the game can be captured as the fixed point of a function f, that is the reward times the discount, as we stated before, for the payoff. And this has been shown to be a monotone contraction. Further, Shapley games is a class of discounted games where each state is a matrix game and the game gives a reward and distribution over the states, and Shapley games can be formulated as monotone contraction, which is an important motivation for our work. Therefore, all the results that we prove from monotone contractions can also be applied to Shapley games. So first we show a complexity-related result that states that monotone contractions lie in the class UEOPL. This is an improvement as the CLS containment that we discussed previously for Tarski and contraction, and also works for non-piecewise linear functions, while the previous restriction was also only for piecewise linear functions. Now, for the three-dimensional case of the monotone contraction problem, we show that we can solve it in logarithmic number of queries, and the algorithm runs in polynomial time, which is faster than the log square algorithm that was previously known for Tarski. Moving and shifting this result to a general dimension by a decomposition theorem, we can show that we can have a log to the power of d over 3 query algorithm for d-dimensional instances. And this also beats the d plus 1 over 2 exponent in the log from the algorithm from Tarski. Therefore, moving the results, as we stated before, the results can also be transferred to Shapley games, and the value can be approximated in this amount of time. A very important component of our work is that of surfaces. If we consider a one-dimensional slice of a monotone contraction, the projective function is as well a monotone contraction, and therefore by applying Banach's fixed point theorem, we know that this has a unique one-dimensional fixed point. Therefore, we restrict ourselves to a one-dimensional slice, and of course the properties of monotonicity and contraction must also hold for this one-dimensional slice, otherwise we would have a violation. All the points in this slice, furthermore, must be pointing towards the fixed point. This is natural because all points must be pointing towards it. Therefore, connecting all the one-dimensional slices, one after the other, of our two-dimensional instance, we get the surface. That surface consists of for each slice, it connects the unique fixed points. And it essentially maps each one-dimensional slice to a height of, this is the height of the unique fixed point in that slice. We have one surface for each dimension, and the fixed point lies at the intersection of all the surfaces. Two very important properties is that surfaces are monotone as well as obey the gradient 1 property. This means that the corresponding function, this is because the corresponding function is also monotone and contracting. Assume that the surface is not monotone, as seen in the figure here. A point that is below the surface, so x, which is below the surface, must be pointing up. Why? Because any point that is along this slice must be pointing towards the unique fixed point, and a similar logic applies to y, therefore y must be pointing down. However, y is higher than x, and the f of y is below f of x. This gives us a violation of monotonicity for the function f, and therefore we know that the surfaces have to be monotone if the corresponding function is also monotone. Additionally, the surfaces must have gradient at most 1. Assume not. Here we have from the point x, which is the unique fixed point of this one-dimensional slice. Here we show the gradient 1 line, and we see that the surface does not obey the gradient 1. Between these 2 points, the L infinity distance is captured as this vertical distance here, and the point y being below the surface must be pointing upwards. However, this gives a violation of contraction for the 2 points x and y, because y is moving upwards while x is being static under f. Which gives us the fact that surfaces must have gradient at most 1 and can move by gradient at most 1, which gives the fact that surfaces must be connected. The up and down sets can now be defined based on the surfaces. The up set is a set that contains all the points where f is pointing upwards in all dimensions, and the down set is a set of points where f is pointing downwards in all dimensions. Intuitively, we can follow the upset to find the fixed point, follow the upset upward to find the fixed point, and follow the downset downwards to find the fixed point. The upset is below all the surfaces here, and the downset is above all the surfaces there. By Tarski's theorem, we get that the greatest fixed point is the supremum of the upset, and the least fixed point is the infimum of the downset. And in monotone contraction, the fixed point lies in between the two. As a warm-up, we present a log square algorithm for two-dimensional Tarski instances. We start in the two-dimensional instance by choosing a slice halfway along the instance, so therefore in the middle, and using binary search to find the region between red and blue. Since red and blue are defining the up and down set and can therefore guide us to the search for the fixed point, we need to place bounds on the red and blue surfaces and use binary search to that end. If the output of the binary search is an upset point, then we rule out the lower half. This is because, as we stated previously, in the upset, all points must be pointing upwards. And therefore, we know that the fixed point cannot be contained below this point. Similarly, if we find a downset point, we can rule out the upper half because the downset pointing downwards states that the fixed point must be below the point that we found. In each of these cases, we recurse, and then we stop when we get to an epsilon approximate fixed point. Each round here spends a logarithmic number of queries to the binary search, and there is a logarithmic number of rounds, therefore leading to the overall complexity of log square for the 2D Tarski. Applying a similar logic to the two-dimensional monotone contraction instance, we again use the binary search principle and suppose our binary search finished for some slice. Now we can transfer the progress to the next slice by moving the bounds along the one vector. This is valid because, as we said previously, due to the gradient 1 property, the surfaces cannot move beyond that. Therefore, by transferring these bounds, we are guaranteed that the bounds will be valid for the next slice as well. We conduct in total a logarithmic number of independent binary searches and carry the progress from one search to the next. We spend a logarithmic number of queries across all searches for the upset. A slight technical detail is that we need to maintain bounds on the downset as well, and we run the up and downset algorithms in parallel. The overall complexity, as stated previously, due to the transferring of the bounds to the next slice, is log 1 over e. Moving to this three-dimensional case, the algorithm for the 3D instances uses the same idea. Therefore, we pick a slice halfway through the instance and spend up to logarithmic number of queries to find an up or downset points and transfer the bounds diagonally from this slice to the next one. However, the problem becomes more complicated in this case because the bounds cannot be simply defined as the interval we had in the two-dimensional case. So what do the bounds look like in 2D slices? It is a natural question to ask. Now, to the two-dimensional instance we saw previously, we add a third color, which corresponds to the third dimension. This is the green seen in the figure here. And anything above a green weak up must be a weak green up. And anything below a green down must be a green down by monotonicity of the red of the third dimension. Therefore, the upset lies below red and blue and above the green, given the monotonicities of each color. A crucial definition in our proofs is that of the critical box. The critical box is a square-shaped box that touches all surfaces and is contained in the upset. Starting from this box, we can define three lobes: one left lobe that contains all points to the left of the box, a down lobe that contains all points below the box, and a diagonal lobe that contains points diagonally above the box. And the critical box, together with these three lobes, is the region that captures all the possible regions where the upset might be contained. Additionally, this box is always a square-shaped. We are guaranteed that the upset cannot be contained in any of the regions that are not captured by the bounds shown here. For a 2D slice algorithm, we maintain an over approximation of a square critical box, and in each step, we perform a constant size grid search on the square and either find an upset point or we find a smaller over approximation of a square critical box. In this case, we can reduce the size of the box, and furthermore, we can reduce the size of the lobes because they start from the box, and therefore we lead to an overall area reduction. We can transfer the bounds to the next slice whenever it's necessary. For the 3D algorithm, given the reasoning we argued just previously, the overall complexity is log 1 over e. And the algorithm additionally runs in polynomial time. Using this three-dimensional case, we show a decomposition theorem that finds the LFP consists of two algorithms. Algorithm A finds the LFP of a D1-dimensional instance in P queries, and algorithm B finds the LFP of a D2-dimensional instance in Q queries. Then we show that composing these two together, we can find the LFP of a D1 plus D2 dimensional instance in P times Q queries. However, the algorithm we presented before finds a fixed point, but it's not guaranteed to find the LFP, so the least fixed point. So we must address this challenge in our algorithm. How can we make this fixed point unique? We see here that the two surfaces, red and blue, might be tracking each other diagonally. In fact, the only way two surfaces might overlap is along the diagonal. In this case, gives multiple approximate fixed points because, as we see here, every point along this diagonal is fixed along the red dimension as well as the blue dimension. The solution to this is first we discretize the problem, which we do throughout this whole paper, so that the surfaces can use integer heights. And in addition, as a second step, we shift one surface down by a half. The surfaces now cannot use the same diagonals anymore due to this shifting, and therefore we avoid the problem of having two overlapping surfaces. The surfaces can only meet at a unique fixed point now, which is near the LFP of the original instance. And this idea, we demonstrated here in 2 dimensions, also works in 3 dimensions. So the 3-dimensional algorithm with the modification that we suggested before that can be reduced to the general case finds the least fixed point, and thus we can apply the decomposition theorem and getting that we can have a log to the power of d over 3 query algorithm for d-dimensional instances while running in polynomial time. As a summary of our results, we have shown that monotone contractions lie in UEOPL, which is an improvement over the previous containment results in CLS for Tarski and contraction independently, and also works for non-piecewise linear functions. And for 3-dimensional instances of the monotone contraction problem can be solved in logarithmic number of queries using the smart binary search and bound transfer ideas that we suggested previously in polynomial time. And this is faster than the log square algorithm of Tarski, as well as giving a log to the power of d over 3 query algorithm for d-dimensional instances, beating the d plus 1 over 2 exponent of Tarski. As future directions, we can, that start from this work, we can look for improved upper bounds for Tarski and contraction for polynomial time algorithms, or for monotone contractions, again, looking into the polynomial time algorithms space. Additionally, an interested direction relating to computational complexity if any of these problems are UOPL hard. Thank you.